Let's look at inverse trigonometric integrals. So remember that if I have the derivative with respect to x of tan inverse, or arctan of x, that is going to be equal to 1 over 1 plus x squared. Similarly, if I have the derivative of arcsin x, that is going to be equal to 1 over square root of 1 minus x squared. Now, I could also include arc cos, but if this was cos, then this would simply be negative, and so you typically don't use it. And that means when we have to take the integral of functions that look like this, we can rely on our inverse trigonometric functions to give us the antiderivative. Let's look at some problems. Let's suppose we had this integral. Now, this almost looks like the derivative of arctan, but there are some differences. Firstly, there's a 5 here, which is simply a coefficient, so that's not an issue. Secondly, there is a 9 here instead of a 1 plus x squared. So we're going to rearrange the function so that it looks more familiar to something that we know. I'm going to take the 5 outside. I'm going to say this is 1 over, and then I'm going to factor out a 9. So this becomes 1, and this becomes x squared over 9. I'm going to rewrite this once again. So this becomes 5 over 9, integral of 1 over 1 plus, I'm going to do more rearranging. Instead of writing x squared over 9, I'm going to write x over 3 whole squared. That's a cube. This is whole squared. So it becomes immediately obvious that we can use arctangent, but instead of x squared, it'll be x over 3 inside the arctan. So let's rewrite this as 5 over 9 arctan x over 3. And the thing about this is that we're not completely done integrating yet, because if we were to take the derivative of this function right here, it should match this exact expression. However, when we take the derivative of arctan x over 3, we would get this expression firstly, and then because of chain rule, we would have to multiply it by 1/3, because that's the derivative of this inside function. So, to compensate for that, we're going to multiply this by 3, or essentially we're going to divide the 1/3 out. So this 3 cancels and simplifies with this 9, so therefore this becomes 5 over 3 arctangent x over 3 plus c, and this is our final answer. Now here is a slightly more rigorous way of doing it, aside from this way, which I consider more intuitive. So let's move this expression down here, and let's say that u is equal to x over 3. Therefore, du would be equal to 1 over 3 dx, and 3 du is equal to dx. Now, our integral can be rewritten as 1 over 1 plus u squared, and instead of dx, we're going to write 3 du. Now, this 5/9 is still here. This 9 is still going to simplify with this 3, and we're still going to get 5 over 3 integral of 1 over 1 plus u squared du, which is exactly 5 over 3 arctan u plus c. Now, if we replace u with x over 3, we will end up exactly matching this expression, verifying that this is the correct integral. Now, this problem looks a little different. We do have a square root of 1 minus x, but there's no x squared term in here. So we're going to rearrange the function and then do a u substitution to make our inverse tangent derivative really stand out. We're going to rewrite this as the integral of 1 over root x, that stays the same, times 1 minus, and I'm going to rewrite x as square root of x squared. So once again, I'm not changing the value, I'm simply rearranging. Now, this becomes immediately obvious as an arcsin derivative, so let's do a u sub to make it even more apparent. Let's say u is equal to square root of x, and therefore du is equal to dx over 2 square root x, because we just differentiate. And as you can see here, we have a square root of x in the denominator, which actually helps us transform from dx to du. Let's rewrite this integral as 1 over 2 root x, because I divided by 2 here, I'm going to multiply out here, times square root of 1 minus u squared, with respect to x still, because we haven't converted it. Now, this dx over 2 root x becomes du, so this becomes the integral 2 times 1 over square root 1 minus u with respect to u, and this is exactly the derivative of arcsin, so it becomes 2 arcsin u. Let's replace u with x, it becomes 2 arcsin square root of x plus c. This is our final integral. Now, this integral can be solved with essentially the same techniques that we used for the first one, but they're slightly more complex. So what we're going to do is we're going to rearrange this once again. 1 over square root of, I'm going to factor out a 3, this becomes 1 minus 4x squared over 3. I'm going to do more rearranging. This is going to equal the integral of 1 over square root of 3, 1 minus, I'm going to rewrite this as 2x over root 3 whole squared. And now I'm going to take this 1 over root 3 outside to make it look simpler. This is going to be equal to 1 over square root 3, the integral of 1 over square root of 1 minus 2x over root 3 whole squared with respect to x. Now, we could do a u sub, but let's simply use our intuition to turn this into an arcsin. So 1 over square root 3 arcsin 2x over square root 3 plus c, but we're not done yet because we still have to multiply. Remember, when we take the derivative of this function, we're going to obtain this expression times 2 over root 3 because of chain rule, so all we have to do to account for that is multiply this by root 3 over 2, or divide by 2 over root 3. Now, the root 3 is going to cancel out here, and all we're left with is this 2 in the denominator. So therefore, our final answer is going to be arcsin 2x over root 3 over 2 plus c. Remember, the c never changes even if I multiply because it is an arbitrary constant, and therefore this is our final integral of this function. Now, in this function, we can recognize that we have an x squared in the denominator, and we have a constant, but it's not in the form that we want. So we're going to have to do some rearranging. And here, we're going to complete the square with this x squared plus 8x to get it in the form of something squared plus some constant. And therefore, that makes it easier for us to use arctangent as our integral. So let's rearrange this, and let's say this is the integral of 1 over x squared plus 8x. Thankfully, in this problem, it's easy because it's 8x plus 16 plus 3. And now this is a perfect square trinomial. So let's rewrite this as the integral of 1 over x plus 4 whole squared plus 3. Let's do some factoring, and let's convert this to arctangent. This becomes 1 over, I'm going to factor out a 3, so 3. This becomes x plus 4 whole squared over 3 plus 1 dx. Let's do some more rewriting. It's the same as the other problems. This will become 1 over 3 times x plus 4 over square root 3 whole squared. Remember, we're not changing the value of anything with respect to x. Now let's put this in terms of arctan. So this is going to become 1/3 arctan x plus 4 divided by square root of 3. We're not done yet. Remember, when we take the derivative of this, we're going to get this expression, but times 1 over root 3. So to account for that, we're going to multiply this by root 3. Therefore, it becomes root 3 over 3 arctangent x plus 4 divided by square root of 3. This I'm going to simplify to make it arctan x plus 4 divided by root 3 all over root 3 plus c, because it's an indefinite integral, and this is our final answer.